Hello everyone and welcome back to the channel. In the world of distributed systems, there is a golden rule. Failures are inevitable. Network go down, servers crash, disk fail, and software has bugs. You cannot prevent all failures, but you can design your system to withstand them. This is the essence of building resilient, fault-tolerant systems. In system design interviews, demonstrating how you handle failures is absolutely critical. Today, we are diving into key strategies for making your distributed systems robust in face of chaos. So, unlike a single monolithic application running on one server, distributed system introduce a new universe of failure modes. When you have dozens, hundreds, or even thousands of interconnected components, databases, microservices, load balancers, caches spread across network and geographies, the probability of some component failing at any time approaches 100%. These failures can be like a partial failures, like a single server crashes, a network link drops, a specific service instance hangs, maybe could be a transient failures like a momentary network glitch, a temporary timeout, a brief resource contention, or a catastrophic failure, which is a whole data center goes offline, for example, or a major power outage. The core challenge is that a distributed system must continue to provide service even when some of its parts are broken. So, how do we design for this chaotic reality? Okay, we do this by focusing on these key strategies for handling failures. Building a fault-tolerant system involves layering multiple defensive strategies, and these are the most important ones. First, we have redundancy. This one, redundancy. The simplest and most fundamental way to handle failure is to have multiple copies of everything. If one fails, another can take over. Implementation for that, we have like n plus 1 redundancy, which is having at least one extra component than strictly needed. Maybe also we can have like some sort of data replication, which basically is strong multiple copies of data. Also, if we have like SR, which is service redundancy, which is running multiple instances of your application services behind a load balancer. The benefit of this one, it eliminates a single point of failures, enables high availability. Next, we have failure detection. You can't react to a failure if you don't know it happened. Systems need mechanisms to quickly identify unhealthy components. The implement of this one, let me just delete this. The first thing, we have heartbeats. It's periodically sending small "I'm alive" message from a component to a monitor. If heartbeat stop, the component is declared as unhealthy. Also, we have healthy check. Basically, load balancer or monitoring systems will regularly ping endpoints of services to check their responsiveness. And 3, we have distributed consensus. Algorithms like Craft or Paxos help nodes agree on who is active leader and automatically elect a new one if the current leader fails. The benefit of that is enables rapid response and automated failover. Okay? Number 3, we have automatic failover and recovery. Once a failure is detected, the system should automatically reroute traffic or bring up new resources without human intervention. The implementation of that, load balancers first, like automatically remove unhealthy instances from their pool and redirect traffic to healthy ones. We can use data replication, like promote a replica to become a new primary if the original primary fails. Number 3, orchestration system, like automatically restore to crashed containers or schedule them on healthy nodes. Lastly, we have DNS failover, reconfiguring DNS records to point traffic to a healthy data center in a disaster. The benefit of that, it minimizes downtime and ensure continuous service availability. Next, we have graceful degradation. The concept of this one, if a non-critical component fails, the system should ideally continue to function, perhaps with reduced functionality rather than completely crashing. The implementation of that, you will use like a circuit breakers, like prevent an application from repeatedly trying to access a failing service, preventing a cascading failures. If a service is failing, the circuit breaks requests, returning an immediate error or a fallback response. After timeout, it tries again. Next, we have timeouts and retries, I would say. It's configure sensible timeouts for external calls, implement retry mechanisms for transit failures, but with limits to prevent overwhelming and struggling service. And I would say lastly, it's bulkheads. It's isolate components to prevent failures in one area from affecting others. Okay. The benefits from that, it improves overall system stability and user experience during partial outage. Lastly, we have monitoring, alerting, and observability. You can't fix what you can see. Robust monitoring is crucial for understanding system health, detecting failures, and diagnosing root causes. The implementation of that, we can collect metrics like CPU, memory, network I/O, latency, error rates, etc. We can log all of that, collect all of these logs, and it traces distributed request flow, and we can also set up alerts for anomalies. The benefits of that, we provide a critical insights for operational teams, helps in proactive maintenance and faster incident isolation. Okay, so how you will handle failures in your system design interviews? In system design interviews, handling failures isn't just a separate section. It should be woven throughout your entire design. I would say you should start with redundancy, like for any critical component, immediately consider how you would make it redundant. Also, you need to discuss detection, like explain how you would detect failures, like heartbeats, health checks, etc. You need to propose automation, detail how your system would automatically fail over or recover. You need to mention graceful degradation, like show awareness of how to protect the user experience during a partial outage. You need to emphasize monitoring, like explain how you would gain visibility into system health. Also, you need to articulate trade-offs. Always discuss how these mechanisms add complexity, cost, or potential latency, but are necessary for reliability. So yeah, that's it for this video, and see you in the future.